Okay, so you had a handout to read on dihydrogen monoxide. And so if you click it, it opens it up or it downloads it for you to read. It's a PDF file. And it just says, it gives you a lot of information. Okay, so I'm going to open it up. So those of you that haven't looked at it yet can see it. So it just gives you, first off, it talks about what it is. Okay, it's a colorless, odorless chemical compound, and it's also got some other different names: dihydrogen oxide, hydrogen hydroxide, hydronium hydroxide, or sometimes hydric acid. So it's got kind of some like other names, but typically it's called dihydrogen monoxide. And you know, it tells you right here, like it's shown to mutate DNA, it denatures proteins, disrupts cell membranes. So it affects a lot of things internally in like humans and animals and living organisms. Then it talks about like, should you be concerned? And it talks about, you know, the government and the CDC, they don't classify it as a toxic or a carcinogenic substance like they do with other things like hydrochloric acid or benzene or other chemicals. But it's part of many known toxic substances, diseases, disease-causing agents, environmental hazards, and can even be lethal to humans in quantities as small as a thimbleful. Those of you that don't know what a thimble is like what you would wear on your like finger as you're sewing, so you didn't prick your finger. So it fits like over the end of your finger. That's how small it is. So there it talks about some research that 86% of the population support a ban on it. Okay, but there's some more information. So some of the dangers. You can die due to accidental inhalation, even in small quantities. Prolonged exposure to the solid form of it causes severe tissue damage. Excessive ingestion produces a number of unpleasant, though not typically life-threatening side effects. It's a major component of acid rain, gaseous. So in the gas form, it causes severe burns. It contributes to soil erosion, corrosion of oxidation in many metals. Contamination of electrical system causes short circuits. Exposure decreases the effectiveness of automobile brakes, so it can cause car crash. If given to vicious dogs involved in recent deadly attacks, so you know there were some dogs that had been given this substance, and then after that they had deadly attacks that they attacked people. It's often associated with killer cyclones in the United States Midwest and elsewhere, and in hurricanes, including deadly storms in Florida, New Orleans, and other areas of the southeastern United States. Thermal variations are a suspected contributor to the El Nino weather effect. And then it goes into some of the uses for it, because it actually is used, it says by industry, government, even in private homes. It's used as an industrial solvent and coolant. Nuclear power plants, the Navy, our United States Navy uses it in some of their older vessels for their propulsion systems. They use it in biological and chemical weapons manufacturing, the development of genetically engineered crops and animals. Home-brewed bombs, it's a byproduct of hydrocarbon combustion in like air conditioning compressors and furnaces. And historically, it was used in Hitler's death camps in Nazi Germany, and it's also been used in other prisons around the world. In World War II prison camps in Japan and China, they used it for various forms of torture. It's even found in like community swimming pools to maintain the chemical balance of the things in the pool. They use it in animal research laboratories, pesticide production. And it's even in these things here that we like would probably be in our homes: food products, jarred baby food, carbonated beverages, fruit juices, in cough medicines and other liquid pharmaceuticals. So any kind of medication that's liquid, usually it's in there. Spray on cleaner, shampoos, bubble baths, grocery store produce sections as a preservative. In the production of beer, coffee, Formula One race cars, even though it's regulated by the Formula One Racing Commission, and it's a target of NASA for planetary and stellar research. And then if you keep going, it talks about that one of the benefits of it is that it actually can improve athletic performance. So those of you, if you're an athlete, maybe that's a benefit to you. So it says, we hear about people using steroids or other enhancement performing drugs. And so, but talks about how no attention has been paid to the performing enhancing qualities of dihydrogen monoxide. It's perhaps the sporting world's dirtiest of dirty little secrets that athletes regularly ingest large quantities of it in an effort to gain a competitive edge. And so it says one technique commonly used by endurance athletes, so people that do like long distance running, like cross country or like cycling, they take a large amount of it immediately prior to a race. And so that's known within those racing circles to dramatically improve their performance. But sports medicine physicians warn that if you ingest too much, it can lead to complications, unwanted side effects, but they do acknowledge that there is a link to that enhanced performance or that improved performance. It's not currently considered a banned substance, so post-race urine tests don't detect elevated or abnormal levels of dihydrogen monoxide. Then it goes through, like, if you overdose on it, what are some of the symptoms that you might see? So it says excessive sweating, urination, bloated, feeling nausea, vomiting, electrolyte imbalance, hypoatremia, which has to do with your blood and your fluid levels in your body, dangerously imbalanced levels of ECF and ICF in the blood, so more blood things, degeneration of sodium homeostasis, so your sodium levels are not normal what they're supposed to be. And it says it could even cause leaking or oozing from the eyes and things like that, allergic reactions and anaphylactic shock, severe chemical depression. It talks about the environmental impact of it, okay? Here's one, a contaminated sewer that has the chemical in it. Contributes to global warming, acid rain, soil erosion. We find it in very high levels in every creek, stream, pond, river, lake, and reservoir in the United States and around the world. It's been verified in ice samples in both the Arctic and Antarctic ice caps, okay? Significant levels were found in the devastating Indian Ocean tsunami in 2004 that killed 230,000 people in all of these countries. And it was also involved in the destruction from Hurricane Katrina that was in 2005 down along our Gulf Coast in New Orleans. Talks about dumping. So companies will dump excessive dihydrogen monoxide and can contaminate, things like that, contaminate our land. So, but none of this is illegal. So it says EPA regulations are in place to make the illegal disposal of DHMO in landfills, but they stipulate that any DHMO appearing in a landfill must be removed. It appears the U.S. government recognizes the danger in some certain circumstances, but it's not banned totally. Like this last part, it says the U.S. government refuses to ban the production, distribution, and the use of it. It may be pressures from private interests, corporate-sponsored economists, among many, and there's a lot of different things. So having looked at that, and there were a couple of websites that you could refer to as well. So you guys were supposed to make a post. Why do you think should or should it not be banned, using kind of the evidence from the handout, or if you looked at one of these websites that had more information. And I gave you kind of some sentence starters to help you, and then you also need to reply to somebody, okay? So what I want to do now is, since we're on our live call, okay, I want to have a little bit of a discussion around this. So what do you guys think about dihydrogen monoxide? Because I've already read some of your, I think we got some more people in the waiting room. Let me let them in. So what do you guys think about, because I've already read some of your replies, but does anybody want to share either out loud or in the chat anything else that you think about dihydrogen monoxide, like, or why did you say what you wanted? Why did you say what you said in your post? Because so far, I think everybody that I've read, they want to ban it. So why are we so adamantly for banning it? Okay, so Luis says because it kills a lot of people. Anybody else want to elaborate on that? And you can type in the chat if you don't want to talk out loud, but
It damages the environment and costs $1 million to fix.
Yeah, so, okay, so here in class, Jose said that it contributes to environmental things, and then Uriel said that it costs a lot of money to fix the problems, right? So it's cost, not only is it like hurting the environment and killing people, but it's also affecting like the economy, because all the damage that it causes that we're having to fix from it, that's a lot of money, right? What else? Anybody have anything you want to add? Anything that you saw that was interesting in the article or on the websites? Doesn't have to necessarily be a bad thing. It could be. So does anybody think that it has any good benefits? Say that again. So Jose said really the only benefit is for the athletes, that part of that section about athletes and enhancing their performance. So why do you guys think it hasn't been banned? What do you think? Why is the government, why are we still letting it be everywhere?
Because it is used everywhere.
Okay, because it's used everywhere.
Everyday items.
Yeah, and even in everyday items. So why do you think maybe the nobody has stepped up and done something to get it banned from those items? Because there are chemicals that like they used to use lead in paint, and then they found out that lead was poisonous because it was they used it on paint on like cribs and walls and toys, and kids were like putting the toys in their mouths or something like that, so they would get lead poisoning. And so they banned lead. You don't use lead in paint anymore to make the colored pigments. So why do you think that we haven't done something like that for this substance? Since we've seen that it's dangerous, it causes all this damage, it causes all these deaths. So anybody else want to chime in here? Mariah, we're talking about the dihydrogen monoxide and why, because pretty much everybody said that they thought it should be banned. So we're just kind of discussing, we discussed kind of some of the bad parts of it, the good parts. So we're discussing now, why do you think it hasn't been banned? Let's see. Stephanie, why do you think it hasn't been banned?
I think it hasn't been banned because there's no really much evidence for the person to ban it because like Uriel said, we use it in our everyday life. So if we take that away, most of the things will be gone that we use.
Okay, so yeah, that's a good point, that if we take it away, would we still be able to have those products?
It would take a long time to take them away.
Yeah, it takes a lot of time to change stuff like that. That's true. Yeah, because if it's like a worldwide global thing, there's a lot of laws that would have to be put in place, and then they'd have to recall products, and they'd have to do research maybe to come up with new ways to make the substances without this chemical. So Mariah says it's usually mixed with something to make it less dangerous. Oh, okay. So you're saying like it's in these other products, so maybe that makes it less dangerous? Okay. So maybe that's why they haven't banned it. Anybody else? All right, so I'm gonna switch over, okay, to.
They use in the military too, the stuff.
Oh yeah, the military uses it.
That's probably why they mostly don't take it away.
So Alex says we've been using it all our life, yet we haven't seen any damage in ourselves, unless the damage is internal, which is true because I believe in one of the websites it talks about that dihydrogen monoxide, they have found amounts or traces of it, evidence of it, in all of the cells, cancer cells of patients who died of cancer. So I don't know that, I don't think I had that in the article, but on one of the websites it does talk about that it's been found. And so after they take tissue samples and they look at the cancer cells, every cancer cell has traces of dihydrogen monoxide in it. So it could be internal, and maybe just like some of us are exposed to it more or less, and then maybe that causes illness in some people and not in others. I'm gonna eat a pretzel. Okay, so I'm gonna switch over to my iPad because I want to share my screen with y'all so we can do this. Okay. All right, so let me mirror the iPad so y'all can see it. All right, so you guys should be able to see the iPad here. Nope, where'd it go? Okay, there we go. All right, can you guys see the periodic table?
Yes.
Okay. All right, so I want to take a look at this. So let's look at this. Okay, we have dihydrogen monoxide, right? That's the name of it, right? The chemical, DHMO, dihydrogen monoxide. So I want to look at this. What element symbol is hydrogen? I'll scoot it up if you don't know. What's hydrogen's element symbol?
H.
H. Okay. So I have H. And what do you guys think this means? This die.
2.
It has a
Two.
subscript.
Means 2, right? And then what element is ox?
Oxygen.
Oxygen. What's oxygen's symbol?
O.
And what do you guys think that this means right here? Mono.
1.
1. So guess what? That's the chemical formula for dihydrogen monoxide. Do you think it's dangerous now? Because what is that?
Water.
That's water.
It's water. I'm gonna have some dihydrogen monoxide today. So why do you think we had that discussion? No, Mariah.
I forgot about that.
I will
I
not
saw
stop.
this video where these people did the same thing to people. They asked, you know, they put water, what they put in water,
Uh-huh.
and they say dihydrate something. I forget the name. They're praying so many people about it. I forget about the name.
Yeah. So the reason that we did that is because that directly ties with our lesson today, because we're doing chemical names and formulas specifically of covalent compounds, because remember, covalent compounds are the ones that have 2 nonmetals, right? So in this example, my 2 nonmetals are hydrogen and oxygen, okay? And so when I have names of covalent compounds, they have these prefixes usually in front of the name to tell me the number of each atom. And so when you go through your lesson today, you're going to see that the first part goes through how to write the names if you're given a formula. And the second part goes through, if you're given the name, how do you write the formula? So part of the reason that we did this today is because all of y'all, when y'all read that article or you looked at those websites, every single one of y'all was like, we need to ban this. It's so dangerous. Like, it's killing people. It's destroying the environment. It's costing us all this money. And I will tell you, nothing on that article, nothing on those websites is a lie. Everything on there is a true fact. So why did you guys all think that we should ban it based on what was on there? What made us think it was so dangerous?
The fact that we kind of sort of never really heard the name like that before, heard it being called like that before in a while, and how it was said in the article.
Yeah, so it has to do with kind of how things were worded in the article, right? Because they made it seem like real serious. They were like, it kills all these people, which is not a lie. It does. When they say accidental inhalation, they're talking about people drowning. When they say that it's the major component of acid rain, well, guess what it is? Because water is the major component of rain. When they say it causes soil erosion, it does. That's what the rivers do. The rivers erode the soil and then it gets deposited somewhere. So nothing on there was a lie. So the point here is that when you read things on the internet, should you always believe them?
No.
No.
No, you should make sure that you do your own independent research first so that you make sure that you are informed, so that you don't get fooled into saying, yes, we should ban water because water is dangerous and it kills people. Because it is true. I mean, there are people that die from drowning. There are people that get burned. So like when it said that the gas form causes burns, that's because if it's steam, it's really hot. And so if you get steam on your skin, it can cause burns. It talked about the solid form causing tissue damage. So the solid form, that would be ice. The tissue damage, that's frostbite, because if it's too cold, then your tissues are going to get damaged. You're not going to get blood flow. So everything on there was true, but the way that it was spun, the way that it was worded, that was intentional. It's intentional to manipulate you into thinking that, oh my gosh, we just need to ban this and So you should always make sure that you do your own research beyond just what's on the internet. Because if it's not a scientific, like trusted source, you probably should not automatically believe it. You should find some actual like academic or scientific sources that can help you understand it, or that can maybe back it up or prove it wrong, or whichever way. And so that's kind of the point of this today, is that if you're not educated enough to understand things, then sometimes you buy into things that people are just saying. People say stuff all the time on the internet, on social media, and people believe it because they don't know better and they don't take the time to do their own research and figure things out on their own. Okay. So I'm going to switch back to our lesson today. So all these people, everybody wants to ban it. Everybody says it's awful. So make sure that you'll still go and reply to somebody on there. So the first part here today, like I said, you're naming covalent, and remember they have kind of two names. They're called covalent compounds. Sometimes they're called molecular compounds because they exist in those molecules. And so what you'll do here on this first part is there's a little lesson here. It's popping up right now. And you're going to be able to name covalent or molecular compounds when you're given the chemical formula. And so kind of a word that we need to make sure we know is prefix, because as I said, prefixes are those little parts, those words that we use at the front of the name to indicate the number, okay? So you have like Shakespeare here, and this is that famous line from Romeo and Juliet. If you guys have not read that in your English classes yet, I don't know if y'all still read it or not. I remember I had to read it in like 9th or 10th grade, I think. But it says, what's in a name? That by which we call a rose by any other name would smell as sweet. So it's kind of like, you know, well, what does a name mean? Because even if you didn't call a rose, it would still smell the same, right? And so we're starting chemical nomenclature, which nomenclature is just the fancy chemistry word for naming things, okay? So the first part today is on covalent compounds. And so it starts off with an introduction for like who came up with all these rules. And you can thank the International Union of Pure and Applied Chemistry, or IUPAC. They are the governing body, the international body that has come up with the standards for how we write names and formulas for elements and compounds. And then it kind of goes through kind of an introduction, because covalent and ionic compounds, they have different naming rules. Today, we are only focusing on covalent. Next week, we will start doing ionic on Monday, okay? So it's just a reminder that covalent, it's two nonmetals, like I just showed you with the dihydrogen monoxide. The two nonmetals were hydrogen and oxygen, okay? With ionic, remember, you're going to have a metal and a nonmetal. So that's kind of the difference. So when you're looking at a name or you're looking at a formula, if you're trying to figure out which of these two categories it falls into so that you know the correct way to write its name or formula, look at the elements in it and look at where they're located on the periodic table. If they're both nonmetals, remember that's everything on this left side, the green side here, and hydrogen. If it's two things from that area, it's a covalent compound. So you'll do the name and formula like we're learning today with the prefixes, okay? If you have a metal, anything here in the yellow with a non-metal in the green, then that's where you're going to do a little bit different, okay? You're not going to use prefixes for ionic compounds. So why are they different? The reason is because when we have nonmetals, because they're sharing electrons, they can form, there's multiple compounds they can form. For example, if I take carbon and hydrogen, there are thousands of compounds that contain only carbon and hydrogen, just in different ratios and different numbers and different amounts. And they're actually their own special category that are called hydrocarbons, because all they contain is carbon and hydrogen atoms. And it can be as simple as CH4, and you'll notice that this 4 is not little. That's because the formatting in this thing does not allow us to do subscripts. But in chemical formulas, all the numbers are those small subscripts, okay? So this 4 is actually kind of a small 4 down kind of towards the bottom of the hydrogen. And so CH4, this is actually called methane. Hydrocarbons actually have a whole different naming system, different than what we learned today. We're just learning basic covalent compounds. If you want to learn more on that, then you can sign up to take IB Chemistry HL next year, because we have a whole unit on organic chemistry where we learn the names of these things, kind of what they're used for. So we learn about, you know, all the like different gases like methane, propane, We do things, we learn about alcohols and how we name them and all their different properties. We learn about carboxylic acids, and things that relate more to like biochemistry, because all of these things like proteins, DNAs, all of those things are made from compounds similar to this that have carbon and hydrogen and then some other elements added in. So that's not part of our lesson. We're focusing just on the basics with the 2 nonmetals, okay? So we might see one like this. So carbon and oxygen, this is within our stuff, okay? Because it's not just carbon and hydrogen. And so, for example, we might have CO and we might have CO2, all right? The image to the right shows how they're different these are. Just adding one more oxygen atom changes a lot of their properties. So this one is carbon dioxide because this 2 on the O. This one is carbon monoxide because there's no 2 here, there's only 1 oxygen. And so this is kind of what their VSEPR structures would look like, okay? They're both linear, okay? They're both in a straight line. How they're both produced by combustion reactions, which that's the type of reaction that we're actually going to learn about when we come back after Christmas break and we start our unit on chemical reactions. But the difference is that carbon dioxide is produced from combustion when you have a lot of oxygen. Carbon monoxide is produced when you don't have enough oxygen. And so that's why carbon monoxide is one of the contributing things to global warming, because when there's not enough oxygen available, like your cars, your engines in your cars, they do combustion. And when you don't have enough oxygen, your car, when it does combustion, it produces some of this carbon monoxide. Or if there's not enough oxygen at all, sometimes it starts producing just regular carbon. And that's when we see like soot and pollution. And so those things are things that contribute to the, destruction of the environment as well. Lighter or heavier than air. Carbon dioxide is a lot heavier than air because of that extra oxygen atom. But carbon monoxide, it's actually a little bit lighter than air, so it floats. Carbon monoxide is flammable. Carbon dioxide is not flammable. Carbon dioxide, if you have very, very high concentrations, you can usually smell it. If it's just a little bit, you usually won't smell it. Carbon monoxide, it can't be smelled or seen at all. It's odorless, colorless, okay? And then dangerous, carbon dioxide, it's not really dangerous. It's only dangerous like if all the oxygen was sucked out of the room and replaced with carbon dioxide, because we need oxygen to breathe. So if all the air in the area you're in, like, if you've seen like movies where somebody's like trapped in they've been like buried alive in a coffin, that's dangerous because you're breathing out carbon dioxide. So eventually all the carbon dioxide you breathe out is going to replace all the oxygen in that little confined space. And that's how you suffocate. Carbon monoxide, though, it's toxic, like even in small amounts. So it says even anything over 50 parts per million. So that's not a very large amount. You're talking about 50 per 1 million parts of air. And so carbon monoxide is actually very deadly. And because it's odorless and colorless, it's and it's toxic in such small amounts to all life forms. There are people who die of carbon monoxide poisoning in their houses, because sometimes what happens is you'll have a gas leak, and sometimes if carbon monoxide is the gas that's being leaked, nobody knows because it doesn't smell like anything. It's different from like methane. Methane gas has a smell, okay? Or propane gas, like for a barbecue grill, those types of gases have an odor. This one doesn't. And so a lot of newer houses and apartments that are built, they have carbon monoxide detectors along with smoke detectors, because that's a kind of a modern safety thing to help with detecting that chemical. So why are the rules different? So covalent compounds, like we said, there's multiple forms they can take with the same element, same 2 elements. But with ionic compounds, because they're transferring their electrons, they can only form one combination because they have those plus and minus charges. And so, for example, sodium and chlorine, they only form NaCl. That only forms sodium chloride, no other compound. And so over here's a couple other examples. These are ionic. And so these are what we'll get into next week. So the red one is the metal. The blue one is the non-metal. And so if I put sodium and fluorine together, this is the only formula it can make, is NaF. If I put calcium and phosphorus together, this is the only formula it can make, is Ca3P2. And that has to do with, we talked about in chemical bonding that all of our charges need to balance out, all those pluses and minuses when we transfer electrons and put them together. And this is showing us now why. And it's because that's the only way to write the formula for an ionic compound. Whereas covalent compounds, there's multiple things going on. So a chemical formula, just to recap, we have the chemical symbols that show which elements we have, and then we have the subscripts. So this tells me that I have hydrogen and there are 2 atoms of it. This tells me I have oxygen, but because there's no subscript, that means there's 1. We do not write the number 1 in our chemical formulas. Having the element symbol there implies that there is 1 of it. So this is our dihydrogen monoxide, okay? So then you have your prefixes. So you need to make sure you write these down so that you have them to refer to. These are what you use anytime you name these covalent or molecular compounds, because the prefix in the name tells you what subscript you're going to use in the chemical formula. That's how they correspond. So some of them we probably know, like, you know, y'all figured out mono and di on the dihydrogen monoxide, because sometimes we've heard of mono in other words or di in other words. Tri is even pretty easy, because usually you think of like a tricycle or a triceratops, okay, things like that. Triangle, all right. Tetra is one that people have trouble with, the number 4. A lot of people want to say quad for 4 because like you're thinking like quadrilateral, like from geometry, but tetra actually comes from, it's actually from a Latin and Greek root as well. Tetra means 4. Have any of you guys ever played the old video game Tetris? You know which game I'm talking about, where they have the blocks and they fall down from the top? Yeah, and you stack them and you're trying to make a whole row and then it disappears, okay? So that game Tetris, the reason it's called Tetris is because all of the shapes are made of 4 squares. So the Tetris, it comes from 4 squares. So it doesn't matter if it's the 4 in a straight line or the 4 that make a box or the ones that are kind of diagonal or the L-shaped ones. If you look at all of them are made up of 4 squares. So that's an easy way to remember Tetris is just think of, or tetra is 4, is just think of that game and that they're made of 4 blocks. Penta is 5. That one's usually pretty easy for people. Penta and hexa are pretty easy because you know pentagon and hexagon, the things that have 5 and 6 sides. 7 is hepta, okay? And 8 is octa, so that's kind of like octagon. That's usually pretty easy. A lot of people have trouble with 7 because that's not as familiar. I will tell you these last 4, hepta, octa, nona, deca, that for 7, 8, 9, 10, they actually correspond to the months of the year. But when the Greeks, was it Greeks or Roman? I think it was the Greeks. Maybe it was the Romans. When they added June and July into the calendar, it threw all the months off. Because originally September was the 7th month, October was the 8th month, November was the 9th month, and December was the 10th month. So they matched up. So September had an S instead of an H here, so it was septa instead of hepta. But they corresponded to 7, 8, 9, and 10, the 10 months of the year. But then they added in July and August for Julius Caesar and Augustus Caesar, and that pushed everything back by 2 when they adjusted the calendar. And so now they don't match up to the months. But originally, like September was the 7th month, October was the 8th month, November was the 9th month, and December was the 10th month because their prefixes and their names came from these numbers originally. So these right here, these are the steps for how you do the name. So it says the first element is named first, no change is done at this point. So we look at 2 examples here, N2O4. So the first element, N, I need to know what element that is. If I look on a periodic table, N is nitrogen. For this second one, C is the first element. If I look that up on a periodic table, that's carbon. So that's the first part of the name. When I go to the second element, you write its name, but you change the ending to IDE. So for example, here, this O is oxygen, but it's going to change to oxide. So now I have nitrogen oxide. This one, O, is also the second one, so that one would also be oxide. So now I have carbon oxide. Then once I've identified the main parts of my names, now here's where I look at the numbers, the subscripts, to use the prefixes. If there's no subscript, it implies the number 1. And then the one thing, this last sentence is very important. The prefix mono, you never use it for the first element. So if the first element is 1, it has no subscript, it's just the element name. You don't put mono on the first one. So here, if I look, the nitrogen has a 2, so that means I would need to use di, because that is the prefix for 2. And the oxygen has 4, so the prefix for 4 is tetra. So now that I've identified those prefixes, I put them in front of the names of the elements that we already wrote. So now I have dinitrogen tetroxide. For this one, we use mono for 1 because there's no subscripts written. However, it's bolded right here. Mono is not used for the first element. So this one is now carbon monoxide. Okay, the mono was only used for the second element, not for both of them. The last step, and you don't have to do this on everyone, you only have to do this on elements that have oxides or compounds that have oxides. If you have an AO or an OO, like see how right here it says tetraoxide, it's got A and O next to each other, and this one is monooxide, it's got 2 O's next to each other. If that happens, and this only happens with oxides, okay, because they're the only ones that start with O, if that happens, then you drop off that last letter of the prefix, okay? So instead of tetraoxide, this is tetroxide, and instead of monooxide, it's just monoxide. So the last, the A from tetra dropped off and the O from mono drop off, okay? Now again, that's only for oxides. Regular elements, you won't have to drop off the vowel, okay? So let's take a look at some practice. All right, so you guys are going to do this on your own, but let's do one together. So this first one, P2O5. So what element is P?
Phosphorus.
P is phosphorus. And then number 2 tells me what prefix do I need for that?
Di.
Okay, so where is diphosphorus on here? Dinitrogen. Here's diphosphorus. So I would drag diphosphorus here. Now the second part, I have oxygen. So what is that going to look like?
Oxide.
Yeah, so remember the second one changes to IDE, so oxide, and then what prefix would I use for the number 5 from that list that we were looking at?
Penta.
Yeah, penta, but because it's in front of the oxygen, the A drops off, so it's just pentoxide. So it's that one right there. And then I'll check, and then it tells me that one's right. So you guys can do the other 3 for your practice later, and then check it, because this is just for you to practice and check. This part, that part's not for a grade. And so then I believe you are done at that point. So once you do that, you'll be done. And then, yeah, no, I meant done with this section. And so there is a little video down here. So if you want to watch this, it goes into a lot more detail. So it goes through the prefixes and he goes through some more examples. So if you're still having trouble after going through the lesson and doing stuff, I would encourage you to watch that. It's 10 minutes long, but you know, it does go over all of that stuff. Okay. The second part is on the next page. The second part, it's really short. It's the opposite direction. This is what happens if I give you the name and you have to write the formula. So it's backwards of what we were just doing. And it's actually a lot easier, okay? As long as you know those prefixes. So if you're given the name, okay, so here we're writing the formula. So we have our little, it says, hey, what's the chemical formula for nitrogen monoxide? And he's like, no. So this one, really, you just have this one page because it's pretty easy. And so there's all these little checkpoints. And so, for example, it says here, the prefix di tells me the subscript for that first element. So di tells me I'm going to have 2 of that element. And here the name is chlorine, so that would be Cl. For the second element, I have hept. So hept is going to be 7. That tells me the subscript for that. And then I have ox. So the only element that would be ox is oxygen. So I'm going to have an O. And then just remember that second element will always end in IDE. Okay. So if I break that down, Cl, and then the di is 2, O for oxygen, and then the hept is 7. That's pretty much it. So as long as you can remember those 10 prefixes, it's pretty easy. The only thing is, just to remember, you don't ever write 1. So for example, if they give you carbon monoxide, that's just CO. If there's no prefix, or if the second one has the prefix mono, you don't write the 1s in the formulas. So same thing on here, you have some practice ones. So let's see if y'all can do this one. We'll do this one together and then I'll let you do the rest of them practice on your own. But what's the chemical formula for dinitrogen dichloride? So between
The second one.
the second one. Okay. Why isn't it this last one? Those both have 2s.
Na sodium, not nitrogen.
Yeah, Na sodium. So be careful. You got to know your element symbols. So make sure you have your periodic table to refer to. And then if you check this one, there it is. And then I can go over, there's some more questions. So there's somewhere you'll type in the words and you can check yourself and practice. Okay. And then when you're done going through all that and you practice and you're feeling confident enough, then you have your little check for understanding where you have both names and formulas. And that's it for today. I will see you guys on Monday where we will start talking about ionic compounds.
Have a good day, Miss.
Have a good weekend, guys.